In this video, we're going to be looking at Hooke's law and pressure in fluids. And this is video 6 of 6 for our forces topic. Next, I recommend that you take the end of chapter test, or alternatively, you can move on to our next topic, waves. Let's get stuck in. Forces are the causes of elastic deformation. When forces compress something or extend something within its limits of proportionality, the object will present resistance. This will then lead to a force being exerted on the object against the compression or extension. Two forces are needed for elastic deformation. In the compression of a spring, there is a force pushing in from one end and another force pushing in from the other end. If there was only one force, then the spring would just move. If a tennis ball was to hit the surface, it would deform to a degree. This is because of the force of weight pulling down and the normal contact force of the ground. Another example is magnets. As crazy as this is, one magnet can be stuck in the middle of two other magnets, and two magnets pulling that one magnet could cause the magnet to deform very, very slightly. Springs and elastic materials undergo a change in shape when forces are exerted on them. The change in length of a spring is known as the extension. For this course, even compressions are known as extensions. A change in shape is called deformation. Elastic deformation is reversed when the force is removed. Inelastic deformation is not fully reversed when the force is removed. There is a permanent change in shape. Elastic deformation has an equation. The extension, or compression, is proportional to the force exerted on the material. The extension of an elastic object, such as a spring, is directly proportional to the force applied, provided that the limit of proportionality is not exceeded. Another way of writing that force is proportional to extension is the following equation. Force is equal to the spring constant multiplied by the extension, where the force is measured in newtons, the spring constant is measured in newtons per metre, and the extension is measured in metres. And this is known as Hooke's law, and you do need to know that. Let's try an example. A spring with constant 5 kilonewtons per metre is stretched by 45 centimetres. Assuming it stays within its limit of proportionality, what is the force which the spring experiences? Well, the first thing we're going to do is write out our equation, and the equation is force is equal to the spring constant times the extension. Well, we know that the spring constant is 5 kilonewtons. 5 kilonewtons is 5,000 newtons, so F is equal to 5,000 multiplied by 0.45. And the reason it's 0.45 is because we'll have 45 centimetre extension, and 45 centimetres in metres is 0.45. 5,000 times 0.45 is 2,250. Force is measured in newtons, so my final answer is 2,250 newtons. Let's try another worked example. A spring is under a force of 90 newtons. The compression is 2 metres. The force is now reduced to 40 newtons. What is the new compression? Now, remember, a constant doesn't change. If you have a spring and you have a constant associated with that spring, the constant will remain the same as long as that spring stays within its limits of proportionality. So we can find the constant in the first circumstance, and it won't change for the new applied force. We can then use that constant for the second circumstance in the question. So the first thing we need to do is work out the spring constant. So we know that the force that this spring is under initially is 90 newtons. We know that the compression is 2 metres. To work out the spring constant, we then have to divide both sides by 2. So the constant is equal to 90 divided by 2, which is 45 newtons per metre. We now know the spring constant, and we can use that in the second part of the question to work out the new extension. So let's write out our equation again. We know that the force is 40 in the second circumstance. We know the constant is 45 newtons per metre from the previous part, and we can work out the extension by dividing both sides by 45. If we do that, we get that the extension is 0.88. Extension, or compression, is measured in metres, so my final answer is 0.88 metres. What are the units though? Well, force is measured in newtons, and I hope that you know this by now because we're on the 6th video of forces, and newtons is the unit for forces. Extension is a length, so we measure it in metres, and the spring constant is force per extension, so its unit is newtons per metre, or N/M. You'll know that compressing a spring requires energy. It is hard to compress because of the resistance. This means you are doing work on the spring. The amount of work done on the spring is equal to the amount of energy stored in the spring, or object's elastic potential energy store. Note this only applied to elastically deformed objects. Objects which are deformed in an inelastic way have more complicated characteristics, and that's beyond the scope of the GCSE course, so you don't need to worry about that. Excuse me. If I was to put in 6 joules of energy to compress this spring, then there would be 6 joules of elastic potential energy stored within the spring. So once I've put that 6 joules of energy into compressing the spring against the wall, it now has 6 joules of energy in its elastic potential store. When a spring is within its limit of proportionality, force and extension are proportional. This gives us a straight line which passes through the origin. And the equation for a straight line which passes through an origin is simple. It's y is equal to mx, where m is the gradient. Where y is the force, and x is the extension, and m is the spring constant. So what is the gradient equal to? Well, the gradient is equal to the spring constant. So if you have a graph where force is on the y-axis and extension is on the x-axis, the gradient of that graph is the spring constant. So, if we look at this force extension graph, we can work out the spring constant. Firstly, draw on your lines to make the measurement easier. So if you pick one point and you pick another point, we can work out the change in y and the change in x. Next, work out the values of change in y and change in x. Well, from 0 to this point here, we'll have a change in y, a change in force of 2 newtons, and we'll have a change in x of 0.2 meters. So the extension change is 0.2 meters, and the force change is 2 newtons. To work out the gradient, we'll use the formula change in y by change in x, and if we divide 2 by 0.2, we'll get 10 newtons per meter. But what if it's non-linear? Well, after the limit of proportionality, F equals KE no longer applies, and the force is no longer directly proportional to the extension. So as you can see by this graph here, we'll have a straight line, and that's labelled Hooke's law region. The force is directly proportional to the extension. After the limit of proportionality, you can see that even when a force is applied, the spring doesn't extend anymore, and that is said to be beyond the limit of proportionality. So now we're going to have a recap back to the energy topic. Can you remember the equation for energy in a spring? Well, here it is. The elastic potential energy is equal to half the spring constant multiplied by the extension squared. And as well as paper 1, this could come up in paper 2 as it appears in both energy and forces. So, you need to know that equation, so I would recommend learning it. If you're following along in your revision workbook, pause the video now and complete task number 22 in your forces workbook. Okay, next we're going to have a look at pressure. Pressure is yet another quantity that you need to learn about in the forces module. Pressure is very simple. It is force per unit area. So, pressure is as simple as that. It's just force divided by area. Where pressure is given in the unit pascals, force is given in newtons, and area is given in meters squared. So let's have a look at a work example. A person's hand pushes against a door. The person's hand is 0.1 meters squared, and she pushes with a force of 90 newtons. what is the pressure between the person's hand and the door? Well, we know that pressure is equal to force divided by area. So pressure is equal to 90, because we'll have 90 newtons of force, divided by 0.1, because our area is 0.1 metres squared. 90 divided by 0.1 is 900. Now, pressure is measured in newtons per metre squared, or pascals, they are the same unit. So my final answer is 900 pascals. And when you write pascals as a unit, you write PA, like that. Let's have a look at another worked example. A book of mass 50 grams is placed onto a table. It measures 30 centimetres by 13 centimetres. What is the pressure which the book exerts on the table? Okay, so pressure is equal to force divided by area, and we also know from a previous video that force is equal to mass times gravity, or the weight is equal to mass times gravity. So we can work out the force which the book exerts on the table by multiplying the book's mass, which is 50 grams, or 0.05 kilograms, multiplied by gravity, 9.8. When you do this, you get a force of 0.49 newtons. So we know that the book exerts a force of 0.49 newtons on the table. Now we need to work out the area, because in the formula for pressure we need force, which we've just got, and we need area, which we still need to work out. So the area is equal to 0.3 times 0.13, and that's because 30 centimetres in metres is 0.3, and 13 centimetres in metres is 0.13. If we multiply these quantities together, we get an area of 0.039 metres squared. So working out the pressure, 0.49 divided by 0.039 gives a pressure of 12.5. And the unit for pressure is pascals. So our final answer is 12.5 pascals. Now, you need to know what a fluid is. A fluid can either be a gas or a liquid. That's what a fluid is, a gas or a liquid. Fluids touch the surface of other materials, and they also exert forces onto these materials at right angles. So if you've got some water in a test tube, for example, then the water will push against the sides of the test tube. But because these surfaces, in this case a test tube, have surface areas, the fluid puts a pressure on the surface. This pressure can be worked out using the normal pressure equation. Complete task 23 in your forces workbook if you're following along with us. Okay, so next we're going to have a look at pressure and liquids. Objects which are put into water sometimes float. This is because the pressure on the bottom of the said object is greater than the pressure on the top, meaning there is an overall upwards force, and this force is called upthrust. So this diagram here shows you what upthrust is. If you've got this cork here in a test tube, you can see that the overall force will be upwards, and this is because there is more pressure below than from up at the top of the cork. This will cause an acceleration upwards. The cork will float. Now, the reason that there's more pressure on the bottom end of the cork is because it's deeper in the water. There's more weight of water acting on those particles of water at the bottom than there is on the top, because it's deeper. So that means the pressure which the cork experiences from the water is greater at the bottom than it is from the top. And if the pressure is greater at the bottom, then it will force the cork to go upwards. And this slide basically explains that. There is greater pressure as you go further down because there is more water particles above you. As you go deeper, more weight is pushing down as there is more mass of water above you. Because of this weight pushing on objects which have surface area, it creates pressure on these objects. If you replace a liquid with a more dense liquid, then there is going to be more mass per unit volume. This means there is more mass overall, meaning more weight and more pressure. Let's have a look at our next equation. The pressure inside a column of fluid is equal to the height of the column of liquid multiplied by the density of the liquid multiplied by the gravitational field strength. So all of these factors can be combined into one equation. pressure is equal to the height times the density times the field strength. Now, the good thing about this formula is you don't actually need to remember it. You just need to know how to use it. So let's have a look at a working example. An object which is 3 meters below the surface of a swimming pool filled with liquid X experiences a pressure of 400 pascals. The gravitational field strength on Earth is 9.8 newtons per kilogram. What is the density of liquid X? Well, we know that the pressure is equal to the height times the density times gravity. We know that the pressure is 400 pascals because it tells us that in the question. We know the height is 3 meters, and we know that gravity is 9.8. Now we need to work out the density of the liquid. So what we can do is we can multiply 3 by 9.8 to get 29.4, and then we can divide both sides of this equation by 29.4 to get 400 divided by 29.4 is equal to our density. That means our density is 13.6, and since density is measured in kilograms per meter cubed, our final answer is 13.6 kilograms per meter cubed. And just a quick note here, this symbol here isn't a P, it's the Greek symbol rho, which is different because it doesn't have the little flick on the P here. If you're following along in your revision workbook, complete task number 24. Next, we're going to have a little look at atmospheric pressure. The atmosphere is the layer of Earth which contains the gases which we breathe and which we need to live. You can see from the diagram, compared to the size of Earth, it really is quite thin. As you rise above the ground, the atmosphere gets thinner. This is because out of the total mass of all the atmosphere, most of it is found in lower down sections. The pressure on the surface of the Earth is biggest because you have all of the mass of the atmosphere on top pushing down. The weight of this is relatively very large, so the pressure is also very large. That's why when you travel up or down hills, your ears can pop, as there is a change in the pressure. Planes maintain a constant pressure within the cabin, otherwise there would be not enough oxygen at the altitudes which planes fly at. If you're following along in your revision workbook, now it's time to complete task number 25. And once you've done that, you've finished. So congratulations, we've finished the forces topic. I recommend now that you take the test and see how much you've learnt so far on the course. I wish you the best.
Thank you very much for watching. Workbooks and test papers which integrate with these videos and online courses are available at our website, backrowtutoring.com.